Hello and welcome to today's tutorial. So today we're going to discuss on the Boolean theorems, and we'll try to simplify a few expressions, logical expressions by using these Boolean theorems, and we'll try to see how we can reduce the number of gates when we draw the logical circuits. Now let us switch back to the screen. Now before going to this Boolean expression or Boolean theorems, so let us discuss on a little bit of the previous tutorial. So in the previous tutorial we were talking about the complements. For decimal systems there is a tens complement and nines complement, and for binary system there is a twos complement and ones complement. Now what exactly is this complement and how this is used is because in the digital circuits there are no representation of the negative, so we will represent this in terms of a positive number itself, but it is the in terms of tens complement for decimal, or it will be twos complement for binary, or sevens complement or ones complement. Now here we have taken one example. So for example, it is 5 minus 2, it is 3, so it is fine, so no issues. So there is a plus 3, so it's right away we can represent. Now for example, if we reverse this case, 2 minus 5, then we know the answer is minus 3. Now minus 3, so minus 3 we cannot represent because we cannot represent this minus. So to represent that, what we will do is let us use the tens complement method here. So I'll just write here tens complement. So it means, so subtract this, subtract end, that is 5 from 9, so we'll get here as 4, and then we will add 1 to this, so this I'll get back again 5, so no problem. So now let us add this 5 with this mini end, so it means 2 plus 5, I'll get an answer 7. So now the 7 is the tens complement form of this minus 3. So to see is it exactly the tens complement, let us find the tens complement of this 7. I should able to get the 3, the plus 3. So it means 9 minus 3, I'll get this as, so I'll get this here 6. Now 6 plus 1, I'll get 7. Sorry, it's my mistake. I'm supposed to do something else. I did something. Sorry for that. So actually it is 9 minus 7. So 9 minus 7 is, we'll get here 3. 9 minus 7 is, sorry. I'm sorry for that. I'm feeling a little rosy. 9 minus 7 is 2. Now 2 plus 1, I'll get back my 3. So now it means the 2 and 3, sorry, the 7 and 3 are in the tens complement form. Now minus 3's tens complement is 7. Now when you convert it back, we'll get it this as plus 3. Now same thing if you want to relate in terms of binary. Now this is okay. Now if you draw the circle and if you want to write this, for example, this is 0, this is 1, 2, 3, 4, 5, 6, 7, 8, sorry, this is 8, and this is 9. So it means from 0, if we go back 3 steps, I'll reach at 7. So that is what it means here. Okay. So now same thing if we do with 9's complement, then we will get to one extra step we will need to take here. So that means that is 9 minus 5 will get 4. Now let us add this 2 plus 4, we will get this as 6. So it means we will get here for 10's complement we will get the result as 7, and here for 9's complement we will get the result as 6. So we will get one value less with 10's complement. So it means here we need to take one extra step in case of 9's complement. That is what it means. Now let us look the same thing in terms of binary. So let us write the binary number for 2. Now it is 0, 0, 1, 0. I'll try to represent this in terms of 4 bits. Then for 5 it is 0, 1, 0, 1. So now we have to subtract this, but we use the 2's complement method to subtract this. I'll remove this. Now to subtract this, first I have to find the 2's complement because I'm applying the 2's complement method for this. So this is 1, 0, 1, 0. Now I have to add 1 to this LSB bit, so I'll get 1, 1, 0, 1. So this is my 2's complement form of 5. Now I have to add this with 2, so 0 0 1 0. So you add this 1 0 1 0, sorry, 1 0 1 1. So then I'll get here 1 0 1 1. So don't consider this as for example, this is supposed to be in terms of hexadecimal, it is um, D. So don't treat it as D. It is the binary number in this form. So this is the -3 in terms of binary. So let us see whether it is exactly the 3 or not. So to find out whether it is 3 or not, so once again we'll take the 2's complement of this number. So we'll get this 0 0 1 0 and add 1 to this because it's 2's complement method. So I'll get back my 3. So this is how we are going to do it. So hope you have understood. So likewise we can also find for 1's complement. So 1's complement I'll get 1 less of this number. So we'll continue with the Boolean theorems. So there are a few theorems which we all have to remember, these Boolean theorems to solve the logical expressions. So before going to this, we will talk about the basic gates, that is AND gate, NOT gate and OR gate. So what is the truth table of NOT gate? So truth table of NOT gate is A and this is A bar. So when we give 0, we'll get it as 1. When we give input as 1, we'll get output as 0. So this is basically a NOT gate. So symbolically we'll represent like this, an inverter in this form. So where we have the input as A and the output as A bar. Then OR gate, if you consider the 2 input OR gate, that is A and B, then its output is A OR with B. So then it is 0 0. If we give the input as 0 0, the output is 0 0 1, we will get it as 1. So 1 0, again it is 1. So 1 1, it is 1 itself because it is logical OR operation, it is not addition. So binary addition is different and logical OR operation is different. So this is the basic OR gate operation. So the OR gate is represented like this symbolically, logical OR gate. So we have 2 inputs, that is A and B. So output is A plus B. Right. Now let us look into the AND gate. So AND gate is nothing but the product of the 2 inputs, that is A into B, logical AND. So then if you have the 2 inputs 0 0, its output is 0, 0 1, its output is 0. It means at any given time, if any one of the input is 0, the output is 0. Whereas in the OR operation, if any one of the input is 1, then the output is 1. So that is the OR gate and this is AND gate. So this we will get it as 1. So if both, when it is 1 0, we will get it as 0. When both the inputs are 1, then only its output is 1. So these are the basic AND gates, basic gates. So we have seen the truth table for each of these. Now we are going to apply these in terms of the Boolean theorem. So first theorem we will talk about is the identity law. So identity law in case of AND form means the product form. It says that 1 into A is equal to A. So how is that? So 1 into A. So consider the value of A is equal to 0. So this is equal to 0. So this is your A. So if 1 into 1, if the value of A is 1, then it is 1. So it means the output is purely dependent on what input you will give in this case. So if it is 1, you will get 1. If it is 0, it is 0. So this is for, that is why it is called as 1 into A. Its output is equal to A. It cannot be 0, it cannot be 1. It is depends on whatever this input, the output is also same thing. This is the indemnity law. Now in terms of OR operation, OR form, let us see what happens. So 0 plus A is equal to, again A itself, because you are performing logical OR operation with 0. when you are performing logical OR operation with 0, so for example, let us take the value of a is equal to 0, we will get 0. If the value of a is equal to 1, then 0 plus 1 is equal to 1. So it means again it is dependent on a. So whatever the a input is there, so a plus 0 is always a. Now let us take the null law. So null law, here if you multiply an input with a logical input with 0, when we take a product of this, so what do we get here? So a into 0 is equal to 0. Anything you multiply with 0, we will get it as 0. So whether a is 1 or 0, it doesn't matter. Now whereas 1 plus a in the R form, whatever may be the input of a, it doesn't matter, because once you are adding with 1, it means it's a logical OR operation, so output is always 1, because 1 plus 0 is 1, 1 plus 1 is also 1. This you have seen in the OR gate operation. When any one of the input is 0 or and other input is 1, so its output is 1. So this is the null law. Now let us look into idempotent law. So here it is, if we take the product of the same input, that is a into a, it is a itself. So a, for example, a, if a is 0, then it is 0 into 0 is equal to 0. If a is 1, then 1 into 1 is equal to 1. Now let us look into the R form. A plus a is equal to a. It means 0 plus 0 is equal to 0. 1 plus 1 is equal to 2. Sorry, it is not 2. Remember, we are not talking about the binary addition. We are talking about logical operation. So 1 plus 1 is equal to logical 1 itself. So it means it is a. So a plus a is equal to a, and a into a is also equal to a itself. Now let us look into the inverse law. So here inverse law says a into a complement is equal to 0. How is that? For example, if the value of a is 1, then its complement is 0. Then we have seen this before, that 1 into 0 is equal to 0 from the AND gate. Now if the value of a is equal to 0, then its complement is 1. Again it is 0. So it means if any one of the input is complement, and if you are finding the product of it, then it will become 0. Now let us look into the R form. So a plus a complement is always 1. So a plus a complement is equal to 1. Why is that? For example, if a is 0, so plus its a complement is 1. So it is 0 plus 1 is 1. If a is 1, then its complement is 0. Doesn't matter. So still it is 1. Therefore a plus a complement is equal to 1, whereas a into a bar is equal to 0. So now let us talk about the commutative property, a very important, most oftenly used. Now there is nothing but a into b is equal to b into a. It means, for example, if a is 1 and b is 0, then it results in the same thing, that is 0. Or you multiply 0 with 1, it again results in the same thing, that is 0 itself. It means a product of b is equal to b product of a. So that is what your commutative property is. So now let us look into the R form of this. So R form says it is a plus b equal to b plus a. It is equal to b plus a. Right. Now let us look into the distributive law. So distributive law says that is a plus b into c a plus b into c is equal to a plus b into a plus c. This is a very important property. So we will show the proof later when we are discussing the examples on this. So this is a distributive law in the AND form. If you look into the R form, then it is a into b plus c. It is nothing but the opening up of brackets. So this can be written as, this is equal to ab plus AC. Next we'll talk about the absorption law. So absorption law is A into A plus B is equal to A. So this again we'll prove it later. And in the R form it is A plus AB is equal to A. So these are again very important. The distributive law and absorption law mostly used in when solving the examples. Next, coming to De Morgan's theorem. So De Morgan's theorem says, so if we take the complement of a product of terms, for example, if we take the complement of A into B bar, so this will equal to, it is the complement of A plus complement of B. So this we can look into like a simple example. Let us take this as A into B as a truth table 0 0 0 1 1 0 1 1. Then we'll take this as A into B bar. So 0 into 0 0 complement is 1. This is again 1, this is 1, and this is 0. Why is that 0? Because 1 into 1 is 1 and its complement is 0. So same thing if you look into this A bar. So let us write the A bar and B bar here, and then we will take the sum of this. So A bar is here 1 1, this is 0 0, and B is 0 1, sorry, this is 1, this is not 1, this is 0. So now B bar is what? This is 1 0 1 0. Now when we add this, what do we get? 1 plus 1, it is 1. 0 plus 1 1. Now 0 plus 1 again 1. 0 plus 0 will get 0. So now when we compare this, so this is equal to same thing. So A into B bar is equal to A bar plus B bar. Now in terms of R form, this can be written as A plus B whole bar is equal to A bar into B bar. It means the complement of R is results in the product of the individual complement terms. Now look into the associative law. So associative law is nothing but A into B. If we take the first product of this and then we multiply this with one more term C, this is equal to first multiplying B into C and then we take the product multiplying with A. So it's both are same. So likewise in case of OR operation, it is A plus B plus C is same as first you add B plus C and then add with C. It is same thing. Next, last one is the involution law. So involution law is nothing but the double complement of A will result in A itself. For example, you take the complement. For example, let us consider A is equal to 0. So then its complement will be 1. Once again you take the complement, it will remain to be 0. So it means the double complement of any term will remains to be same. So this is the involution law. Now let us look into some of the proof and examples here. So I'll shift this page, go to the new page here. Okay. So here we have to prove A plus B into C is equal to A plus B into A plus C. Now while solving these kind of logical expressions, we have to use all the Boolean theorems that we have discussed before. So now first let us open up the brackets here. So that is, we'll get A into A plus AC plus AB plus BC. Now from the previous theorem, A into A is nothing but it is equal to A itself. So let us rewrite this. So this will result in A plus AC plus AB plus BC. Now just think about it, what is the next that we can do from this? Now if you see in the first three terms, A is a common, so take A as a common term here. So A of 1 plus C plus B. Now from the previous theorem we know that 1 plus anything is equal to 1. So this is from the identity, this is from the null law, and this we have plus BC. So now this is equal to A plus BC. So therefore we have proven that right hand side is equal to the left hand side. So A plus B of A plus C is equal to A plus BC. Now let us take one more example. Save this. Let us discuss on the absorption law. A into B plus C. What do we get? So this is equal to AB plus AC. That's it. Now what about A plus AB? So A plus AB is equal to 1. So how is that? Sorry, A plus AB is equal to A. So A plus AB equal to A, this is from the absorption law, from the previously what we have discussed. So now this is nothing but just take A as a common. So what do we get here? So we will get here 1 plus B. So 1 plus B is nothing but it is 1. So ultimately it is A into 1 equal to A itself. So therefore the right hand side and left hand side it is same. So now let us see what is A of A plus B. So this is actually equal to A. So how is that? Let's prove. Now A into A plus A into B. So then A into A is nothing but it is A itself. So A plus AB. Now once again let's take A as a common. So what are we left with? So we left out with 1 plus B, with A is nothing but again, so 1 plus B is equal to 1. So ultimately it is A, which is equal to the right hand side, that is A itself. Let me clear this section. Now likewise there is A plus AC, again we will get it as A. So now if there is, let's take some interesting example here. So let's take it as A plus A bar B plus A B C bar. So we have to simplify this. I'll tell you what is the reason why do we need to simplify these gates, these equations, the logical equations, because okay, fine. So before going to further simplification of this, let us understand why we have to simplify this. If we want to construct the logical circuit using this expression, this is some expression which is equal to f, alright. So this is some expression which is equal to f, or output y. So if I want to draw the logical circuit for this, then I'll take the lines here. So then I'll call this as A, B, C, and I'll take here, I'll put the thick dot so that it shows the connection. So I'll apply a NOT gate here, so that is A bar. So likewise I'll put the NOT gate, and here I'll get it as one more line here. So this is C complement. Now let us write the circuit here. So it is A complement. So I'll take this A complement into B. So I'll take from the B input. So I have to perform the AND operation here. So after performing the AND operation, I'll get here the output as A bar into B. Now there is a one more product term here, that is AB into C bar. So AB into C bar is nothing but, I'll take this from here. So I'll take the B input from here and C bar I'll take from here. So then I'll take the AND of it, I'll apply the AND gate. So I got here A, B, C bar. And finally I have to add all these terms with A. So let us add all these terms with A here. So I have to take one more A from here. So I'll take this. So take the OR gate. Fine. So this is my final output, F or Y, whatever you want to call it, you can call it. Now how many gates we have used? So two NOT gates, two AND gates and one OR gate, right? So there are so many gates. Now by simplifying this logical expression, we can reduce the number of gates that we can use in the design of the circuit, digital circuit. That is why we always used to simplify these Boolean expressions. So now let us simplify this expression and see. Let's see what do we reach and how many gates do we require. Now if you look this term here, so A is a common term, so let us take the A common here. So I'll get here 1 plus B into C bar. So 1 plus B into C bar is nothing but it is equal to 1. So I left out with one more term here, that is A bar into B. So then I'll get this as A plus A bar B. So A plus A bar B is nothing but, this can also be written as A plus A bar into A plus A bar into A plus B. Let us rewrite this and see. So let us write this as A plus A bar. So A plus A bar into A plus B. So basically I should get the same thing here. First let us check it whether it is right or not. So I'll get here A into A plus AB plus A bar into A plus A bar B. So here A into A is nothing but A here, then plus AB plus A into A bar is nothing but 0. So plus I'll get one more term here, that is A bar into B. So from this I can take B as a common term. So when I take this as a B as a common term, I'll get here as A plus B of A plus A bar. So A plus A bar, we know that it is 1. So this is equal to 1. Therefore, ultimately, we will reach to a solution that is A plus B. So it means rather than using two NOT gates, two AND gates and one OR gate, I can simply write this as one OR gate, and this is equal to my F output. So this is A and B. So there is no, the third input is not at all required for this output equation. Are you all listening? So today very few participants have logged in. So this will be reported to your dean. Just inform to your friends. Your attendance will be strictly monitored through your login sessions. Any doubt so far? So we have to use a little sense here, like this expression we have added here. So this we have used little sense and we have added this so that we can reduce it further. Okay, so now let us see one more example here. Let me save this page. Okay, so let us take one more example, that is let's say F or Y is equal to A plus A bar B plus ABC plus A into C bar. So we have to simplify this. The ultimate goal is to simplify this as much as possible so that we can reduce the number of gates in the design. So now if you look into this term, the first and the third term, what is the common? The common is A. So let us take this A as a common. So I'll get this as 1 plus B into C. So I have the left out terms are A bar into B plus A C bar. So this 1 plus anything is equal to 1. So I'll get it 1 here. Let us write this. So I'll get here 1 plus A bar B plus A C bar. So like as before, I can write this again in terms of before going for that, what is the next step? So if you can see in these two terms, A is common again. So let us take the A as common in these terms. So I'll get here 1 plus C bar, which is equal to, so it is not equal to, plus A bar into B. So again, I am left out with the last term, that is A plus A bar B, like how we have done for the previous case. A plus A bar B can be written as, I can multiply again with A plus, this can be written as, I'll write like this, A plus A bar, A plus A bar into A plus B. So this we use the properties are Boolean theorems, and we are applying that. So when we write this, so finally we left out with the term that is A plus B. So you have to remember these relations so that we can straight away apply these relations whenever the situation comes. So now let us look into one more example. Okay, so next example is A bar C plus A into C bar. This is a very simple one. I'll let you to tell me the answer. So please tell me what is the final answer of this. So how do you proceed for this? There is no common terms to proceed. So first what you will do is, first you have to break the bar. So there is a certain property that from the De Morgan's theorem, when we break the bar, so the plus, the AND operation becomes OR, and OR operation becomes AND. So it is A bar into C plus, so this will become your A bar plus C bar. This is what you get, and if you see the first and the second term, A bar is common, so take it common, so A bar, so I'll get here as 1 plus C plus C bar. So finally we'll get this as A bar plus C bar. So this is the answer. Now let us take a little complicated one. So let's take this as B plus C bar into B bar plus C plus A bar plus B plus C bar, whole bar. So to simplify this, first we have to open up these brackets, and here we have to break this bar. So then we will get this as B into B bar plus B into C plus B bar C bar plus C into C bar plus you break this bar, so you'll get A double bar into B. This is OR operation, right? So I'll get here B bar into, we'll get C double bar. So remember, A double bar is nothing but it is A, so I'm going to erase this. C double bar is nothing but C, so I'll erase this double bar. So now it is A into B bar into C. So now look into the common terms where you can find it. So what about this term, B into B bar? So B into B bar is nothing but it is 0. So now which are the common terms that we will take here? And here one more term, that is c into c bar, is also 0. So now the left out there are only 3 terms, bc and b bar into c bar and a into b bar into c. So we'll take this and this term, then what will happen? Let's see. So b bar into c bar plus, which is a common term in this, so we'll take c as common, so I left out with b plus a into b bar. So from the definition, from the theorem, we can write this is equal to, it is nothing but b plus a into b plus b bar. So when we simplify this term, we'll get this is equal to b plus a into c. So now when we open up this bracket, so we'll get this as bc plus ac, and here we have the term b bar into c bar. So this is the final simplification, and if you want to further simplify, then we can take c as common, but it doesn't make any sense further. Okay, so that is the last step. And likewise, there are quite a few examples that you can work out, but I'll leave it to you. Now we will move on to the next section. If you have any queries, you can ask. So like this, you will be given a Boolean expression in the examination and asked to simplify. And sometimes there might be multiple solutions for the answers, so you have to be very careful while simplifying this. You may stop at some point where some more steps could have been proceed, and we could have reached the better result. Okay. Now let us see, in the exam it is asked to prove this, say f1 is equal to a plus b into c bar. So they will ask you to find the final output y from this using the truth table. So they will ask you to construct the truth table and find the output for a plus b into c bar. So to do this, we know that there are 3 inputs here, that is a, b and c. So that we'll write here, then what is required, then c bar is required, so let us write c bar. Then what we require is b into c bar, then we can add this term with a and we can reach to final term. Okay, so now with 3 inputs we will get the 8 levels. So let us write the truth table for this. It looks like an octal table, so that is 0 0 0, then 0 0 0 1, then 0 1 0, then 0 1 1. We have to write all possible inputs, 1 0 0, then 1 0 1, then 1 1 0, then all triple ones. So this is what we have to do. Now we'll take the c complement here, so this is 1 0 1 0 1 0 1 0. Then b into c bar, so this is my b, so b there is 0 into 1 is 0, 0 into 0 is 0, 1 into 1 is 1, 1 into 0 is 0, 0 into 1 is 0, and 0 into 0 is 0, and here 1 into 1 is 1, then here that is 1 into 0 is 0. So I got this. Now final term is we have to add this with a, so 0 plus 0 0, so this is my final f, then 0 plus 0 0, 0 plus 1 1, then 0 plus 0 0, then 1 plus 1, sorry, 1 plus 0 0, then 1 plus 0 1, so 1 plus 1 1, so 1 plus 0, it is 1. So this is the final output for this given expression. So like this you can put any expression and you can find it. So in the examination it may ask you to prove the De Morgan's theorem using the truth table as well. So I'll save this page. So for example, what is the De Morgan's theorem? So one of the De Morgan's theorem is that it is A into B whole bar is equal to A bar plus B bar. They will ask you to prove this, might be using a truth table. So for this is a 2-input case, so we have 4 inputs, 4 possible inputs. So then A into B, we'll write all the possible inputs, that is 0 0 0 1 1 0 1 1. So now we need A into B bar, so we'll take this A into B whole bar. I'll write straight away, I'll skip one step. Then we'll write this A bar, then B bar, and finally I'll write one more here, that is A bar plus B bar. So basically this and this should match results. Now let us see. Now 0 into 0, 0 complement is 1. This is 0 into 1, its complement is 1. So this is also 1, this is 0. So now what is A complement of this? This is 1 1 0 0. Now this is 1 0 1 0. Now let us add this. Now 1 plus 1 1. This is 1, this is 1, and this is 0. So now if you see this A into B bar and A bar plus B bar, both are matching. So likewise, they will ask you to prove any of these kind of equations in the examination. You should be able to do it. So there are quite a lot of examples here that you can work out with. Okay, so here we'll wind up our session. In the next session we will talk on the digital circuits. We'll look into the basic universal gates, basic gates and then universal gates, and we'll try to solve or design the other gates using the universal gates. Okay, so thank you.